see the more complicated example. If we have a spherical object with a uniformly charged distributed Q inside, the question is that if we want to calculate the electric field at this point P, what is the electric field here at this point? Okay. Again, we can use the Gauss law for this problem. But first, we have to look at the symmetry of this problem. We can see that this problem has spherical symmetry also. It means that if you are on a spherical surface, that has the same center as the object, okay, and at this point that we want to calculate the electric field, or on any point on this spherical Gaussian surface, you can see that when we look back to the object, we will see the same picture. That is, we see a sphere, okay, and we see the same charge because the charge is uniformly distributed on this object. So it means that we should have the spherical symmetry, and from this symmetry we can assume, we can expect at least two things. First, the magnitude of the electric field is constant on the spherical Gaussian surface. Okay. The magnitude of E should be the same on the spherical Gaussian surface, which is concentric with this object. Okay. And we can expect the second expectation that the direction of the electric field direction of E point okay, if we assume that this is a positive charge, okay, if we have a positive charge, the direction of E point outward let's say like this. in the radial direction. Okay. If in this case, like in this case, Q is a positive charge, so we can expect that this is the direction of E, which is point outward in the radial direction. But if Q is negative, we can expect that E is point inward in the radial direction. Okay, it depends on the sign of Q. Anyway, in both cases, you can see that from this assumption, from this expectation, E will always parallel to the vector dA. Okay, E is always parallel to the vector dA. So the consequence of this expectation is that E dot dA is equal to the E times dA. Okay, so once we have these two expectations, the calculation is quite simple because we can use the Gauss law. 3E is equal to the integral over the closed surface E dot dA, which equal to the integral of over the closed surface E dA. But from the first expectation, we can take E out of the integral because E is a constant. So we have that this is equal to E integral dA. But what is the integral dA? Again, integral dA is equal to the surface area of the Gaussian surface, and in this case, it is a spherical Gaussian surface. So we have E times 4 pi r squared, where r is the radius of the spherical surface. This is r. But we know that the flux from the Gauss law, the flux is equal to the net charge Q over epsilon 0. From this calculation, we have that E is equal to the Q over 4 pi epsilon 0 r squared. So this is the magnitude of the electric field on the Gaussian surface. The magnitude of electric field on the Gaussian surface, and also the magnitude of the electric field at the point that we want to calculate at this point. Okay. You can see that we have the identical form of the electric field of a So it means that if you have a charge uniformly charge distributed on a sphere at any point outside the sphere, the electric field is equal to the electric field of the point charge if we have all charge. I mean, if that point charge is centered at the sphere and have the charge equal charge to the net charge of the sphere. So it means that if you collapse all charge to the center, if you collapse all charge to the center, the electric field at this point will be from the sphere will be equal to the electric field of the point of this point charge at the center. Okay. Please notice that in this case, we choose the spherical Gaussian surface. This is because our problem has the spherical symmetry. Our problem has spherical symmetry, allow the center of this object, right? We have the spherical symmetry around the center of this object, so we choose the spherical Gaussian surface which has the same center or concentric with this object. Okay, so we use the symmetry to simplify our calculation because we have these two expectations, and at the end we get the result quite simply. Okay.